Welcome back. Our second speaker today is Elizaveta Levina from Michigan, and she'll be talking about concentration of random graphs and community detection.
Thank you, and thank you for the introduction, as well as thanks to the organizers for the invitation. This is joint work with Roman Vershinin, who is a probabilist known in random matrix theory, and our joint PhD student, Can Li. All of this work was done when we were all at Michigan, but they have since moved to warmer places. And I know that the reason I'm here, and the reason probably most of you are here, is to hear about concentration of random graphs. But since communities and networks is my part of this work, and this is something I know more about, I thought I would also tell you about that, also because it'll be more different from what you might otherwise hear in a random matrix talk. So I will start with the networks and the motivating application and problems that arise in network analysis, and then I will get to concentration, and then I'll come back and tell you what concentration tells us about the problems we want to solve as statisticians. So very briefly, what are networks? Start from the very beginning. Mathematically, it's just a graph, so it's a collection of nodes and edges. That's all there is to it. In statistics, when we say network data, we think about data on relationship between entities. So traditionally in statistics, you collect data about one entity. So say if you have people, you might know their age and gender and height and weight and things like that. That's about one person. Data on relationships is about two people being friends or co-authors or whatever they are. It's data on relationships. And especially in the modern day of big data everywhere, there are lots and lots of places where data like this arises and is analyzed. Facebook and other social media is the example that comes to mind. Of course, where the nodes are users and the edges are their friendships, but there are many other examples that come up in science, like in real hard science, where people also want to understand issues in networks, and these are just a few examples of where people have actually applied these methods and studied them. In ecology, people study ecosystems, representing them as networks, where nodes are animal species and edges are predatory-prey relationships. So basically, which species eat which other species. That's a directed network. And for survival of ecosystems, balance is important, so that's something people look at. In, say, in transportation, you can look at networks of direct flights between airports. Political scientists are getting into analyzing networks now. This may be questionable as a real scientific tool there, but they're definitely data, and they look at relationships between countries, which could be trades, deals, conflicts, all sorts of things. So this really arises in a lot of domains. Just briefly, notation. Any network can be represented with its adjacency matrix, which is just a binary matrix telling you whether there is an edge going from node I to node J. In this talk, I will focus entirely on undirected networks. So the edge has no direction, and therefore the matrices will be symmetric. So you go from a graph like that on the left to a matrix like this. And one thing that I also want to get out of the way up front is self-loops. A self-loop is an edge from a node to itself. So that's if you have a 1 on the diagonal. In many practical contexts, it's not possible to have self-loops. Say, like, you can't be your own friend, even though you could send yourself an email, for example. So it depends on the context. But it's really convenient to ignore them mathematically, because otherwise you have to be writing a special case out all the time. So I will ignore them. I will just treat them as any other entry of this matrix. So what are communities is the next question. There is unfortunately no precise definition, mathematical or otherwise. It's one of these things like clustering and statistics. People have a feeling of what it is, but it's not actually well defined. All that I can really say, and all that people say, is that it's a group of nodes that in some sense is more similar to each other than to other nodes. That's not a very satisfactory definition, but that's kind of the starting point. Often people think of communities as groups of nodes that are tightly knit within themselves, so groups of friends, more links within the community than links to the outside. But that doesn't have to be the only kind of community. A simple example is genders in a dating network. There will be a lot of connections between groups, so other things are possible. And of course, by the time we get to concentration, I will give you a mathematical definition of what we will do in that particular problem, but there is no universal definition. And the problem of community detection, possibly slightly misnamed because it's not really detection, it's estimation, is assigning each node in a network that you've observed to a community. Typically, this means finding a partition, so each node goes into one and exactly one community, although now there are extensions where communities are allowed to overlap. Some nodes can be outside of all communities, etc. But for the purposes of this talk, we'll be thinking of a partition, so one each. And this is a very interdisciplinary research area. There are many people from physics and computer science who have worked on this and other areas. As statisticians, of course, we take a particular type of approach, which they don't necessarily do, which is we think of probabilistic models. We think of models that generated this data, and then we try to fit the models to data, and that's how we learn communities and whatever else we want to learn. Now, I want to show you some examples here because the very first question you may ask is, well, how do you know that your model works, right? What is the ground truth here? How do you verify that whatever algorithm you're using actually makes sense? And it's true that in a lot of cases you don't know what the truth is, you can't predict, but there are a few examples where A, these communities really exist in real life, and B, people actually know what they are. So these are very classical, famous examples, so I'll just tell you about them. The Karate Club is a very well-known network. It was collected back in 1977, back when they recorded these things by direct observation of actually observing people interact and not from their social media. And this is a student club where they were doing karate, so this network was recorded, and very luckily for the person who was studying it, there was a conflict in the club, and the club split into two. And half the club followed, so the square nodes, one is, I think, the instructor, the other one's the manager, so there were two leaders, they went their separate ways, and the people followed each one. So the colors represent who they followed, so you know how they split, and that's being used as the ground truth. Here's another interesting example from a paper that studied dolphins. Dolphins had motion trackers attached to them, so they were studying them in their natural habitat and their natural interactions. And there was a group of dolphins, they were all interacting, and then there was this special dolphin, the yellow one, who at some point went away and disappeared from this herd. And then these two groups marked in different colors completely stopped interacting. They actually separated, they geographically went to different places, and all interaction has stopped. And even more interestingly, over a year later, this dolphin came back, rejoined them, and they started interacting again. So nobody knows what the function of that particular dolphin was, but this happened. So again, there is an instance of ground truth. And then from more modern times, and this really is more from the media, but sometimes people make this effort. This is another well-known data set about blogs about US politics. As you can imagine, they're very easy to label. They come in one of two kinds. And the people who collected this data, they're sort of information people, they manually labeled each one. The edges here represent blogs linking to each other on the web. So again, here the ground truth is available. So in a few cases, we can really see what is happening, and this is what these things look like. Okay, so let's go back to models and probability. So what kind of models are there? We think of A as a random binary matrix with zeros and ones. Very commonly, independence of edges is assumed, and that is also what I'm going to assume. And I really don't know how to get rid of that, even though I would really love to, because in practice, that's not plausible. Another typical assumption that people make is exchangeable networks, which basically means that the distribution of the adjacency matrix is independent of your labeling of nodes. Who you call person number one and who you call person number two is immaterial. You can switch the labels. The distribution is the same. And I will also assume that throughout. And then the way we think about it is the information of interest is contained in the expectation. Right? This is a matrix of probabilities because the edges are binary. And that's really what we want to know. Somewhere there's all the information of interest. Everything on top of that is noise, just random realization. But of course, we only have one A, right? We have a single realization of this matrix, so we can't estimate this expectation very well unless we assume that there's some shared information across these probabilities, right? So some sort of structure has to be present, whether it's low rank or block constant or whatever, or communities. You'll see that we'll get to communities. In order for this problem to be at all meaningful, something has to connect these different entries of A. And what we want to do is understand properties of both the models that we might dream up and also algorithms that we use to fit them to real data. And the typical question here is, what happens under different scaling regimes? So I'm going to suppress the dependence on n, just so I don't have to write this n every time, but this is how we think about it. There's the matrix P, which is the expectation of probabilities, but really, as the number of nodes grows, this matrix is also growing. And we assume that there is a scaling factor that affects everyone in the same way, and then there's some constant matrix P which encodes structure. So there is structure and there is density, and there are two different things. All right, so start from the simplest model there is, the Erdős-Rényi graph, which we can denote as GNP, and nodes probability of edges is the same for all edges. It's P, so they're just IAD coin flips. Except for symmetry in the matrix. Half the matrix is IAD coin flips. And this is a beautiful mathematical object. It's very well studied. A lot is known about it. And it doesn't fit any network data that there is ever been recorded. But a lot is understood about it. And in fact, looking at the properties of the Erdős-Rényi graph already gives us some inkling as to what's going to happen when we move on to more complicated models. So I'll just briefly mention it. All the nodes have the same expected degree. Basically, everything is the same. The node degrees follow the binomial distribution, and this does not happen because in real networks there are hubs. There are nodes with much larger degrees that this would allow. But people know a lot about this, and in particular, they know that if degree is less than 1, the expected degree is less than 1, then the graph has hardly anything in it. There are no connected components of size more than log n, so the problem is hopeless. There's nothing to look at. There is the important transition that happens when d is exactly 1. You get a largest connected component, which will have the order of n to the third nodes, so you're capturing something now. And when it's greater than 1, you have a giant component, which just means the size of the largest connected component is order n. So there's a sharp phase transition at 1, and no other component is comparable in size. And then there is another sort of phase transition that happens at log n, which is isolated nodes. So if you're below log n, then almost surely your graph will have isolated nodes. And if you're above log n, then it almost surely will not. So it's a very interesting set of properties people have learned about it. So partly this leads us to different asymptotic regimes that we will look at when we get back to our community detection. The degree less than 1, basically people don't really consider it because there's nothing to do, there are no edges. When d is a constant greater than 1, so it doesn't grow with n, it's O of 1, this is what we call sparse. The fraction of isolated nodes doesn't vanish, so they'll still be there, but the question is, can you do something? Can you do better than random guessing when it comes to communities? And then there are these two regimes. So one is when the degree grows, but slower than that log n, which is the next important transition. I'll call that semi-sparse. The graph is almost surely disconnected, but it's a lot better than the sparse case. And then if it grows at least as fast as log n, we'll say that's semi-dense. And then if the degree grows proportionally to n, then we'll say it's dense. And this case, again, is not interesting. It's too easy. Everything becomes trivial in this case. So really, the three interesting cases are here. And in the real world, generally, networks tend to be sparse. It's hard to claim that degree grows with n. Right? The billion users of Facebook, right, probably doesn't mean the number of your personal friends is proportional to a billion, right? The things are much more local. So sparsity is working well for sparse networks is definitely a desirable property for all sorts of algorithms. So here is an example of a simple model with communities. It's probably the simplest model with communities, now very well studied. It builds on the Erdős-Rényi graph, and some properties are inherited from the Erdős-Rényi graph, which is why it's good to review them. The way you generate a network from this model, the way you can think about it is first you basically roll a die for every node and you get a label. So you draw that from a multinomial distribution with some probabilities for each value. You do it independently, so that's like colors of these nodes. Once you know there are colors, you generate edges conditional on the labels with some probability that only depends on the color of the node and not on anything else. So if I tell you one's blue, one's green, then you know what the probability of edge is going to be. So all the information is really contained in a k by k symmetric matrix of probability of connections, no longer n by n, which is big, and k by k, which is small. But we don't know these colors. We don't observe the labels. All we observe is A, which is just the edges. So the problem then is to estimate C and B and pi from the observed matrix A. And in this case, it's very clear what communities are. It's just nodes that have the same label. That's a community. You can write this in this other way, which will just make it very clear why spectral analysis is useful for this kind of problem. If I just arrange my membership information for each node into vectors of length k, where I'll just put a 1 in the place that corresponds to the community it belongs to and zeros everywhere else, then I can stack those things. So each row is a membership vector, so it's 0, 1. This is an example with just two communities. I can stack them this way, and then I can write the big matrix, P, as this product, which it's not quite the eigendecomposition because of scaling, but it's almost the eigendecomposition. And you can see that the eigenvectors of this matrix will be where the information is. So just as a simple example, this is as simple as the stochastic block model gets. Just two communities, everything's balanced and symmetric, so just P and Q here, probability of connections. And you can just compute this explicitly. The two eigenvectors, it's a rank 2 matrix. The two eigenvectors are a constant and something with half plus ones, half minus ones. So you can just read the community information of the second eigenvector. You don't even need to do any other algorithm. If you can get this eigenvector, you're done. And in general, if you have k communities, more than 2, then you need the first k eigenvectors of this matrix to recover the community information. How do people actually do it? They don't quite read it off, and there are maybe more than 2 communities, so just looking at one eigenvector is not enough. The standard way to do it, and a very, very popular way to do, is spectral clustering, say on the adjacency matrix. Spectral clustering does 2 things. First, it computes the k leading eigenvectors, which is where all the information is, and it arranges them into a matrix n by k. And then it runs the k-means clustering algorithm on the rows of that matrix. So the rows correspond to nodes. K-means clustering is a very, very popular standard clustering algorithm. If you don't know what it is, it doesn't really matter, but I'll just quickly tell you. The way k-means clusters things is it starts from an initial value that just selects k points randomly to be cluster centers. Then for each data point in the data set, it assigns it to the nearest cluster center. So now each point is in its own cluster. Then the centers are replaced with the means of the points that have been assigned to them, and then you iterate until convergence. So there are some guarantees about this algorithm. It works under some conditions, not always. It does depend on the initial value, of course, in practice. So it's not perfect, but it's quite reliable, and it works in a lot of cases. So this is how people do it very frequently. And another way to do it, which actually is usually more practical, is to do it not on the adjacency matrix itself, but on the graph Laplacian. Graph Laplacian can be defined in multiple ways depending on where you come from. You can define it through diffusion on a graph, through random walks on a graph, through many different things. For the purposes of community detection, the most useful one is the symmetric normalized Laplacian, which is defined this way. You normalize by degree, basically. D is a diagonal matrix where you put the degree of every node in the diagonal. And since we only care about the eigenvectors, we don't really need this identity minus. We can just look at this matrix. So I'm going to call this the Laplacian, even though technically it's just part of that. So in theory, spectral clustering either on the adjacency matrix or the Laplacian gives you the correct result under the stochastic block model. And as the saying goes, in theory and practice are the same. In practice, they're not. So in practice, that's not true. In practice, the Laplacian tends to work better. And the reason this happens is because the SBM is also a pretty simple model, and degrees are often more heterogeneous than the SBM will allow. And then because you normalize by degree, that helps. But strictly speaking, since I'm just talking about the stochastic block model, this shouldn't make a difference. So when does it work? Going back to the question of can we have performance guarantees? Can we understand the properties of algorithms and the models that go with them? If you think about what you really need for a method like this to work, there are sort of three components that you have to have if you want to show that something is good for this problem. First of all, of course, you need a model where communities are in the eigenvectors, right? Because that's what spectral clustering does. It takes the eigenvectors. If the information is not there, then obviously spectral clustering is not relevant. So you need a model where communities are encoded in the eigenvectors, and the stochastic block model is such a model, so that's good. And then that's what brings us to concentration. You need concentration because the information is in the expectation of A. It's not an A. So you need to be able to guarantee that the difference between what you observe and what you want is not too large. And then once you have concentration, the Davis-Kahan theorem basically gets you home, because if you have concentration, then the eigenstructures will also be similar by the Davis-Kahan theorem. And so then you recover the information. So this is how we end up talking about concentration, because we basically need to be able to say something about this quantity. And the main challenge for concentration, not surprisingly, is sparsity. That's when it's hard to get concentration, either for the adjacency matrix or the Laplacian. We know in practice as well that spectral clustering tends to fail if the network is sparse, and hopefully I'll be able to tell you more about the reasons why it fails. And of course, below some level of sparsity, everything will fail, right? As we saw, there are no edges, nothing is connected, so forget about it. So it's not a question of whether it will fail for sparse graphs. Eventually, everything will. But the question is, where does it fail? And where is the transition, and what can you guarantee? So the key questions become, when does A concentrate? When does this binary matrix concentrate around its expectation? And the second question is, if it doesn't, can we fix it? Is there something, some regime, where we can do something to make it concentrate again? So that's the two questions that I want to focus on. Let me, just to help you get some intuition about this, let me show you some pictures. Back to the simple example with just two communities. Everything is balanced. There are three key parameters that control the difficulty of the problem in this case. The expected degree. The more it is, the more edges you have, the easier your problem. Then there is this quantity which we call out-in ratio. That's basically the ratio between Q and P. Of course, the smaller it is, the easier the problem. Right? There's a big difference. And then number of nodes. K remains fixed. So remember all asymptotics only as n grows, but not k. So of course, the more nodes you have, the more information you have about each community, the easier the problem becomes. So just to help you get a sense of what these things look like, 800 nodes, pretty low out-in ratio, so relatively easy case. And there are networks for degrees from 1 to 14. So this looks hopeless, right? There's a ton of isolated nodes, nothing is happening. And even by the time you get to 5, this already looks very clear. So it seems like you should be able to estimate it. This is what the adjacency matrices look like. And when you look at the adjacency matrix, you can see it even here, right? Even with the degree equal to 1, that's pretty clear. You'd think that I should be able to get that. But of course, that is not what you observe, because this is ordered correctly. What you actually observe look like this. This is the matrix in the first row with randomly permuted nodes. And just for comparison, look at this third row. The third row are all Erdős-Rényi graphs with the same number of edges. So in the second row, there's community structure, and the third row is not. And that's hard to tell, right? You will need concentration in order to be able to actually get out of that problem. So let's go back to spectral clustering and try to understand why it fails on sparse graphs. Clearly has something to do with not enough edges, right? So what does it do? So let's look at this one, same setting, so just 80 nodes so we can see them. Degrees 2, this is what the adjacency matrix looks like. So you see there are some isolated nodes and there are also some isolated edges, just a couple of little connected components here. If you look at the eigenvectors, remember in principle, it should be the second eigenvector where you see the solution. Here it's actually the fourth. Here it is, right? Half up, half down. Of course, noisy, and the isolated nodes you can't do anything about. It doesn't load on the eigenvector, but this is the solution. But it's not coming, and this is the constant eigenvector, which should be first, but it's not showing up there because these two weird things are there. And if you think about what they are, of course, they are just going with these little connected components, right? There are eigenvectors that load on just these tiny blocks and nothing else. So that's what breaks concentration for K. Now, you might say, okay, isolated edges, let's throw them out. Let's look at the largest connected component. Will it then work? Will it be okay? Because that would be easy to fix. And indeed, for this example, if you look at the two leading eigenvectors of the largest connected component, they look fine. They look like what you would expect. Constant and half up, half down. But that's a small network, and that's actually not always going to be the case. So let me bump up the size, go to 800 nodes, slightly increase degree to 3. So this is just the largest connected component of the graph. Happens to have 737 nodes. So you can see the colors are labeled here. So let's look at the eigenvectors. And again, this is what the first one should look like. This should have been second, but it's not because there's this weird spiky thing in the middle, even though everything is connected. So just being connected is not enough. So let's see where this comes from. If I label the nodes that correspond to that spike, you find, I don't know if you can see the yellow, you find this little part of the graph. That's called the dangling tree. So it's something very sparse. It just attaches at one node, but it's basically enough to generate an eigenvector that just picks up that and doesn't do what we want. So connectedness is not enough. There's more that we need. So now let's talk about concentration. So what we want, what the key requirement here is, so we can apply the Davis-Kahan theorem, is that the difference between A and its expectation is not too large. Now, what does that mean? Well, relative to the expectation of A in that same norm. This is all in the matrix spectral norm. So this is what we have to compare. Now, a lot of work has been done on this, including by the chair of our session. And in the paper, we were careful to trace the history, but I don't have time to do this in the talk, so I'm just going to tell you about what we know now, or at least what we knew as of like a month or two ago. This is a very rapidly moving field, and people keep proving things all the time. So I'll state all the results for the inhomogeneous Erdős-Rényi model, which is very different from the Erdős-Rényi. Inhomogeneous means the probabilities can be different for every edge. And that's very general, that all I'm really assuming here is independence of edges. Binary edges that are independent, but these probabilities can be anything. So this is more general than communities and the stochastic block model, but of course it includes the stochastic block model and the Erdős-Rényi graph, and in fact many other network models that I haven't talked about. So all the results will be for the inhomogeneous Erdős-Rényi graph. And everything that I say will be with high probability, of course, although I won't say with high probability every time, but just any statement you see, assume that says with high probability. So first of all, dense networks concentrate. This was very well known for the Erdős-Rényi graph a long time ago. Bayes' law is something that people have known for a long time. That already for the Erdős-Rényi graph implies that this difference is less than 2 square root of d. D is the expected degree. But what we now have, and this is one of our contributions, is for the inhomogeneous graph, this holds. It's root degree plus root log n, whereas the expectation itself is on the order d. So in particular, log n comes out here. If the degree is bigger than log n, then this term can be ignored, and root d is smaller than d, so it concentrates. And in fact, this is optimal. You can't make it smaller than that. So dense networks concentrate with log n or higher. That's good. Sparse networks do not concentrate, and you should expect that, having seen the pictures. Even for the Erdős-Rényi graph, so I mean, once you prove it for the Erdős-Rényi graph, it's a negative result. You don't have to prove it generally. Even for the Erdős-Rényi graph, this was known. This is much bigger than d, which is the order of the expectation. And this actually happens because with high probability, there is a node with a large degree, which blows up concentration. So if the degree is of 1, if it doesn't grow, and this difference is going to be at least log n, so you can't get concentration. And then the third important thing is sparse networks can be made to concentrate if you regularize them appropriately. For the adjacency matrix, the problem with concentration is caused by high degree nodes. So in theory, again, you can do something simple like just throw out all the nodes with high degrees. Then the network will concentrate, but in practice, of course, it's a really terrible idea because that's where your information is. You already don't have many edges. So if you throw out the highest edges, it'll be even worse. So it's another place where theory and practice diverge. You could do something more conservative, which is not throw anything out, but just change the weights to bring down large degrees. But since spectral clustering and the Laplacian tends to work better, I'll just talk about regularizing the Laplacian instead. Okay. Before we go to the Laplacian, I will just very briefly tell you the main tools that went into this concentration result on dense networks. The basic construction is first you find the part of the network on which it concentrates without any regularization. Turns out this part is big. And Grothendieck factorization is Roman's current favorite tool, and this is really key to doing this. And then you show that it's well behaved on these rows and columns, and then you repeat. And in the end, you end up with a picture like this, where you construct something that concentrates without regularization that's really big, and then the rest is small. I don't want to talk any more about this, but just to give you some idea of what the tools are. So concentration of the Laplacian, which is the one that we actually want to do, the result is at the high level the same. Again, it concentrates if the degree is at least log n, and it fails to concentrate if it's of a smaller order than log n. So that's the same. The problem for the Laplacian is actually caused by the opposite. It's caused by low-degree nodes, not high-degree nodes, or these dangling trees or isolated nodes. But the end result's the same. It still fails to concentrate. So multiple methods have been proposed to regularize the Laplacian. I will just focus on one. This happens to be from my own group, but it's also a very simple one. So easy to explain. So the idea of this regularization is before you compute the Laplacian, you take the adjacency matrix and you add a small constant to every single entry. This is a vector of ones, so this is just a fancy way to write a constant, and this constant is small. This gives you the scaling. This row is just a number between 0 and 1. What's the intuition behind that? Of course, if you add something big to every entry of your matrix, you've destroyed all structure, right? That you just made it a constant. But if you add something small, you no longer have isolated nodes, right? Everything has a weak connection. The graph is actually fully connected, but weakly enough, so you still have the structure. And that's the idea behind this regularization. So the concentration result, writing it this way, there is some tau here. What we have shown is the regularized Laplacian will concentrate. And, well, there's the one extra step. You have to compare the expectation of the regularized matrix to the expectation of the actual matrix you wanted. But these are non-random matrices, so that's a lot easier than random matrix stuff. So it concentrates. So let me show you how it solves this problem with the dangling tree that we have already seen. This is what we have already seen. This is the spiky second eigenvector that happens if you don't regularize, if your row is 0. And then you add a constant, and it's still there. They just switch places. It basically inflates the eigenvalues the right way so that the order switches. And the nice thing is it doesn't really matter how you choose this constant once you got the scaling right, because then you can go through changing the value of row, and it'll slightly change, but basically you get the first two eigenvectors are correct. So it really kills that spiky one, which is what we didn't want. So in the time that I have left, I'd like to tell you a little bit about specific results for community recovery that this that this concentration implies. Mostly I'm going to follow an excellent review paper. Actually, it's a monograph now. It's 160 pages long by Emmanuel Abbé at Princeton. So not all of it, by no means, is our work, but this is how you bring in concentration and you get results on the actual community recovery. So the way we're going to measure recovery is by this disagreement quantity. So if C are your true labels, C hat are the estimated labels from whatever method you use, you basically count the fraction of nodes on which they disagree. But because the labeling itself is meaningless, right, what I call community 1 versus what I call community 2 doesn't matter, I also have to minimize over all possible label permutations. But this is just permutations of k things. So that's my disagreement. Just think of it as classification error, basically, if you like. And there are different modes of recovery that people talk about in the literature. And here, statisticians and probabilists use different names. I, being a statistician, will use statistical names, but I'm giving you both, so you can match if that's the literature you know. So detectability, or probabilists call it partial recovery, is just better than random guessing. You cannot recover them all. You cannot recover them asymptotically correctly, but this disagreement is smaller than what you would get by chance. Weak consistency, or almost exact recovery, means this disagreement goes to 0 in probability. Strong consistency is a stronger statement, or it's called exact recovery. You get everything right with probability going to 1. So there are no mistakes. So what do we know for the SBM? Just to make the results more palatable, I'll state them all for k equals 2. That's when they're relatively easy to understand. Most of it is now available for general k, but it's much uglier to look at. But this condition is hard to relax, so it's just P and Q. This is symmetry, but can be relaxed. In some cases, it gets even uglier. This is substantially harder to relax still, as communities of equal size make things a lot easier. If they're unequal, that's much harder. So you can see the gap between theory and practice here too, right? Even though so much progress has been made in terms of realistic scenarios, we still don't have everything. But for k equals 2 in the symmetric case, these are really quite beautiful results. Detectability, which was first conjectured by physicists out of their physics considerations and then proved by probabilists, is just this simple phase transition thing. If you scale the edge probabilities as A over n, B over n, this is what you need to be able to do better than random guessing, and this is sharp. Weak consistency will hold if this goes to infinity, no matter how fast. Strong consistency, and see here log n appears, so you need, here you need degree to grow, here you need degree to grow at least as log n, and this is less beautiful, but again, this is a very simple formula, and there is achievable with a polynomial time algorithm greater than square root of 2 and then less than square root of 2, it's impossible. So they're really quite sharp results that people have now. Specifically for spectral clustering, so that didn't tell you anything about the algorithm, right? That was about the model and the density of the graph. So I say, okay, with a polynomial time algorithm, maybe we don't know what it is, maybe we do. So specifically for spectral clustering, what do we know? And we know quite a bit. So for spectral clustering, in the sparse regime, where the degree is a constant, regularized spectral clustering can detect communities up to an arbitrary fraction epsilon, as long as this holds. So it's the same fraction greater than some constant. So if you compare it to this, the difference is just a constant. So it's optimal up to a constant, but we don't know. This is something that we proved, but we don't know if it can be brought all the way down to 1, maybe. In the semi-sparse regime, when the degree grows, but not necessarily as fast as log n, you can achieve weak consistency, so that's enough for weak consistency. But if you want strong consistency, you need to be in the semi-dense regime, so you need the degree at least of log n or more, and then both of these are optimal. So spectral clustering actually gets you all the way down to the optimal limit, to what is possible in that regime for that model. And then if you're in the dense regime, if your degree grows like n, the problem is trivial. So yes, spectral clustering works, so does everything else. So that's not so interesting. So this is what we know. And just some take-home points. Even for the stochastic block model, which practitioners agree is not particularly realistic, there are problems that remain open, such as growing number of communities, unbalanced community sizes, different algorithms. So that's even for the stochastic block model, but even if we could really answer every question about the stochastic block model, it's still going to be too simplistic for many real networks. And as soon as you move into the more sophisticated models, of which some have now been proposed, not many results are available of this nature. From my personal perspective, I think one of the biggest challenges is getting rid of independence of edges when you look at network analysis. And that's because, especially if you look at social networks, the property of transitivity is universal. And that basically means if A is a friend of B and C is a friend of B, then A and C are more likely to be friends, right, if they have a friend in common. That is not independent edges, right? So, but random matrix theory doesn't get us very far if we don't have independence edges. So that's just sitting out there, and I don't think it's going to get solved anytime soon. But even if you don't go there, if you're very ambitious, maybe you can try. But even if you don't go there, there are many promising directions for future work on this intersection between probability and statistics and network modeling. I'll stop here.
Thank you very much. We have time for one question.
Okay. I would like to know about if you can mention some results on model selection for the number of communities. I know a paper by Peter Bickel and colleagues. I don't remember all the names.
That's a very good question. I didn't talk about this at all. I just treated K as fixed, but there is in fact a large literature on the question of how to select K. I think the paper you're referring to is more like hypothesis testing approach. There are also, like I have a paper with a student, there are also approaches based on the spectrum. If you look at the right matrix, you can calculate certain things from the eigenvalues this time, not the eigenvectors, that will let you estimate it. There's a variety of methods, but it's definitely an important problem. And of course, these results are true for the correct K. If you plug in an estimated K, that's no longer directly applicable. Yeah. Yes.
Nice talk. So the notion of accuracy, you had this strong and weak consistency, and then the sharpness. Is anything known on convergence rates, right? I mean, like in classification, we would talk about optimal convergence rates.
Yes, that's another good question. That's a question for Harry Zhou, of course. And they do have some results showing some minimax optimality. And the thing is that to do that, you need some very tricky algorithms if you really want to talk about rates. And they have to be two-stage. So you can do something like spectral clustering first, and then you have to sort of like improve locally to make it work nicely. But yes, there is some work on that. I just didn't talk about it.
Very little questions. Can you consider, or would you consider, or maybe you did consider different models of random graphs? Not only the simple GNP.
Well,
GU.
Right. So, well, all the concentration results that I stated in the second half apply to the inhomogeneous Erdős-Rényi graph, which means any random graph with independent edges. So it does include quite a lot of models. The models that are more based on how the graph was generated, right? The various percolation things and power law generating networks, all those things. No, we haven't looked at that. That would be a good thing to look at. The thing is that this is all about comparing the matrix to its expectation. If your random graph model is defined in terms of the generative process, it becomes a more complicated thing. And my interest was from communities, so not so much, but that's definitely something people could look at.
So, well, in the interest of time, let's thank our speaker again.